Okay, let us start with the review what we have done last week. So we are discussing traffic stream, right? So traffic stream is made of what? Traffic stream is made of what are the elements of traffic stream? Huh?
Individual driver and vehicle.
Drivers and vehicles. And these drivers and vehicles are affected by what? What affects drivers and vehicles? What affects traffic flow?
Above vehicles.
Huh?
Above vehicles. Above the vehicles.
Traffic is made of vehicles, right? Now what affects vehicles? Flow of vehicles. Demand, okay.
Behavior of drivers.
Behavior of drivers, okay. What else?
Signal, for example.
Huh?
Signal.
Signal is what? Part of? Signal is part of the road, right? So road design. And what else? Last thing. Anything else which affects traffic flow? So vehicles affect each other, road affects the traffic flow, and what else?
Drivers.
Traffic is made of vehicles and drivers, right?
Yes.
Done. Anything else? Check.
Weather.
Okay. Huh?
Also the weather.
Weather, environment. Okay.
Maybe signals.
Done. Finished. Okay. Now, then we divided the streets and highways into two types. Traffic facilities or streets and highways. What are the types? Interactive and interactive. Okay. And macro and micro was what? Parameters, traffic parameters. Within each type, macro and micro, we discussed how many parameters? Three. Okay. Three macroscopic.
Speed,
Volume. Huh?
density.
Density. Okay. And again, there were different types of volumes. Daily, hourly, flow rate, all of them are in volume. Okay. And there were two types of speeds as well.
Space means speed.
Space means speed, time means speed. Okay. Three microscopic.
Speed, headway, spacing.
Speed, headway, spacing. Okay. Which speed now is this?
Time.
One car. Speed of one car. One vehicle, one car. Whatever. Okay. And we looked at some equations as well. So if you have a spacing, you can calculate what?
Density.
Density. If you have headway, you can calculate
Flow.
flow,
Volume.
flow rate. Okay. And then we looked, the last equation was this one where you can even calculate the speed as well. Okay. Moving on. So let's say we have a congested multi-lane highway which has an average spacing of 200 feet and headway of 3.8 seconds. Okay. And we have to estimate the rate of flow, density and speed for this lane. Okay. So spacing and headway is given and we have to calculate the three. Which type is this? Macro or micro? Macro. Okay. All three of them are macro. So what is spacing?
The distance between two vehicles.
Yes, front.
Any same point. Okay. And what is headway?
The time between two vehicles.
The what?
What is the one way?
Huh?
The time of two vehicles plus one way.
Passing one point. Yeah. Okay. Now we have a spacing. From a spacing we calculate what? Density. This one. Okay. So if the spacing is 200 feet Then density is how much? Okay, so if spacing is 200, dA is 200, then density is 26.4. Okay, what units I am using here? What are the units? Vehicle per mile per lane. Who told me it's per lane? Where is it written? Where is it written? There's only one lane. Did they give the number of lanes? Did they mention it's a one lane highway? Or two lane or three lane? Number of lanes are mentioned? Not mentioned. Okay. So how did I include number of lanes here in the equation? So how do I know it's per lane? Because of because it's spacing. Average or not average, it's not the point. Spacing is between two vehicles which are in the one lane. You cannot be between two lanes, right? In two lanes it can be 0. Two cars can go together. So if you are measuring spacing, you have to measure it between two cars in one lane. You cannot do it in multiple lanes, right? So spacing by default is what? One lane. So you use spacing to calculate something, it will be per lane. Okay, so it's default. Got it? Clear? Okay. Now, then they ask for rate of flow, right? Okay, they gave me headway and they are asking for rate of flow. This is the equation. What's the rate of flow here? How much?
9%.
Again, you can see the units: vehicles per hour per lane. Flow, rate of flow always per hour. Rate of flow always per hour. Okay, that's how we call it the rate. It's the hourly rate. And per lane, why? Because headway. Again, cannot be between two lanes. Clear? Any question? Okay, the third thing they are asking for is speed. What is this dA?
Average spacing.
Spacing. What is HA? Height. Okay, so you already know these two things. This one is 200, this one is 3.8. Okay, so how much is the speed? And you already have the conversion as well. Huh? 25 point? Should I add per lane here? No? Why not? The speed cannot be per lane. So
They're all distance over time.
distance over time. Okay. Oh, okay. Yeah, we don't write per lane, never. Okay. And we write per lane with density and flow because with number of lanes it can increase. So density in one lane is 26, in 2 lanes it will be 52, double, right? Okay, in 3 lanes it will be. So if you keep on adding lanes, you are also adding vehicles. Okay, so it can increase. Same thing with flow. From 1 lane I can pass 1000 vehicles, in 2 lanes I can pass 2000 vehicles, and so on and so forth. So with number of lanes, density and flow can increase. The speed, whether it's this lane or this lane, doesn't matter. Okay, you cannot say 1 lane 35, so 2 lane will be 70. It doesn't happen like this. Okay, we wish. Now, this is another equation which is the basic equation of traffic flow. Okay, this is the main, the basic, the most important equation of traffic flow. Okay, now this equation shows you what? V equals to S into D. V is what? V. Volume. We are using a small v here. So what does it mean? Rate of flow. Okay, small v is rate of flow. S is speed. And D is density. Now which speed are we talking about here? Huh? No. Which is speed? We have space means speed, time means speed, speed of one vehicle. Which one is this?
Speed of one vehicle.
No. Space means speed. Huh? Because it's macro. You see, all 3 parameters are what? Macro, right? Okay, so it cannot be for one vehicle. Okay, and it cannot be time minus speed as well, because we don't use time minus speed with these parameters. We always use space means speed. We always use space means speed. Okay, now I showed you the units for all 3 of them, right? What are the units for speed? mph is what? Mile per hour, right? So they are the distance. Okay, and if you go back to the definition of a space means speed, this is speed over a segment. Segment means it's a distance, right? I have a distance. In this much distance, this is the speed. In this section, this is the speed. What are the units of density? Vehicle per mile. So again, they are the distance, right? They are the distance. What are the units for rate of flow? Vehicle per hour. So there is no distance, right? Distance is gone. Okay. Yeah, it's cancelled. But what will happen here? What we have been saying, even now, I said what? If these 2 are macro, then this one should be macro. Okay. If you are calculating density or flow rate using headway and spacing, then you have to use average to make it macro, right? So you cannot have 2 parameters which are of different kind and 1 parameter which is of different kind. So if these 2 are same over the distance, space means speed is over the distance, right? Same speed. Density is over the distance, same. What about flow? I can have flow on the starting point, on the end point, on the midpoint. There is no distance involved, right? So I can get flow at any of these points, and I may have different values because I am counting cars, right? Okay, cars which are passing me. Okay, so I may get different values. So then how will this equation work if these 2 are not changing, S and D is not changing, and V can change? It doesn't work like this, right? If I put these 2 values, I should get the same answer every time, right? Okay. So how do I make sure about it in the field? How do I make sure the flow doesn't change as well? So you have to put a condition on the segment on which you will apply this equation. What's the condition? Condition is the whole segment should have constant characteristics. The design of the section should not change. For example, number of lanes. Okay, so if I have 2 lanes, it should be 2 lanes from start to end. Another example, gradient. If I have 2% gradient, I should have 2% from start to end. If you change any of these things, the point at which this thing will change, the flow will also change. So the whole equation has to change. The whole equation has to change.
But there is no intersect. There is no intersect.
There is no intersection, yeah. Intersection is part of the section. The intersection comes, again the section has changed, right? It's not the same section. So due to any reason, if the section changes, this equation will interrupt. This equation will cut. Okay, so from here to here, up to half of the section, there were two links. So up to half of the section, you can apply S and D and you can get the value of flow. It will work on all the points in the half. After that, something has changed, section has changed. So now you have to find S and D again because the flow has changed. So you will get a different value of flow. So whenever something changes on the section, you have to recalculate the equation. Got it? Clear? Any question? Okay. Yeah, one more thing. This equation works in stable flow conditions. Stable, the flow is continuous. Okay, it's not stopping. The flow is not stopping. Okay, when does the flow stop? At the signal. Okay, or what else? Traffic congestion. Okay, so in those conditions this will not work. The equation will not work. So there are two conditions for using this equation. One is you have to use it on a uniform section, on a constant section. Okay, and the other one is it has to be stable flow. Okay, if the flow is starting and stopping, like in a queue or traffic jam or signal, this equation doesn't work. Clear? Okay, two very simple question. Now remember the equation is what? V equals to S into D, right? Rate of flow equals to speed into density. Look at the first question. If a free lane were observed to have SMS of 55 miles per hour and density of 25 vehicles per mile per lane, what will be the flow rate? Simple. What is SMS? Space means speed. Okay, don't think the highway received an SMS. Okay, it doesn't. So SMS, space means speed, and what else is given? Density. Now you do what with them to get flow rate? You multiply. V equals to S into D. And what will be the units of V? Vehicle per hour?
Vehicle per hour
Per lane. Okay, why? Because this is per lane. Okay. You use something per lane, the answer will be per lane, right? Got it? Okay. Look at the second question. Freeway lane with a measured SMS of 60 and flow rate of 1000. Now what do you do with this? You need density. You have what? Speed and flow rate. So now you do what? You divide flow rate upon speed. Okay, this equation, right? So now they gave you V and S. They are asking for density. And the units will be vehicle per mile per lane. Okay, again because. Okay, can you do this? Simple, right? Okay. Now we look at these three curves. These three curves explain the relationship between pair of macroscopic parameters. Okay, between each pair we have drawn a graph. Okay, so the first one on the top between flow and density. So what happens to flow when density changes? Second one between flow and speed. So what happens to flow when speed changes? And the third one between density and speed. So what happens to density when speed changes? Okay, so you can see the effect of one on the other. Okay, so what is it showing here? I'll start with this one, the easiest one. When density is 0, the speed is maximum. Okay, Why? Density 0 means no vehicles on the road. So the speed is supposed to be high, highway is empty. Okay. Density reaches maximum. The speed becomes 0. What happened on the road? Traffic jam. Okay. So we call this as jam density. Maximum density is called as what? Jam density. Clear? Okay. Now look at this one. We start from here. Okay. Flow is 0. Density is 0. So no cars on the road, no flow. Highway is empty, right? Okay. No car is on the road, so nothing is moving. Clear? Okay. Density increases. Flow increases. More cars are on the road and they are moving. Okay. So if somebody looks from the top, he will see more cars, and if somebody is counting, he will see more cars passing. Okay. Till you reach what? Maximum. But maximum, this is what? Maximum flow. Capacity is what? Maximum flow. Capacity is maximum flow. Okay. Maximum density was what? Maximum density is jam. Okay. This is why in every section I am asking 3-4 times. Capacity is maximum. You say it. Capacity is what? Yeah. Okay. So after capacity, if you put more cars on the road, it will start to have traffic jam. Last week we did one example for peak hour factor, if you remember, where there was a capacity for 15 minutes, and if we have more than that, then the extra cars were creating a queue. The extra cars are creating a traffic jam. Okay. So you already reached capacity. Now you are putting more cars on the road, or more cars are approaching the road. Will the capacity increase? No. It will remain the same. Okay. So the cars which are above capacity, what will they do? They will create a traffic jam or a queue. Okay. And this queue will do what with the remaining flow? It will slow everybody down. So this is why the flow, you see, after capacity, what is happening? The flow is going down. Okay. This is the effect of the congestion, the traffic jam. Okay. So density increases even after capacity, but that doesn't mean the flow will increase, because the flow has already reached the capacity. So this extra density is now slowing down everybody. It's creating a queue. Okay. And this queue is decreasing the flow. Okay, got it? Clear? Okay. Last one. We start from here. The speed is maximum. Flow is 0. Why the flow is 0? There are no cars. There are no cars on the road. Highway is empty. So your speed is supposed to be the maximum. Okay. Now what will happen? If the flow increases, the speed will decrease. Okay. So the flow will keep on increasing until it reaches what? Maximum. Maximum flow is called as what? Capacity. Maximum flow is capacity. And after capacity, what happens? If you still have more vehicles, it will start to have a queue and the flow will reduce. Okay, the flow will decrease. And obviously the speed is also decreasing. Even in a traffic jam, the speed is going down. Okay, the speed doesn't go back. Clear or not? Okay. Now, this speed, the maximum speed, whether in this graph or this graph, we call it the free flow speed. It's written in the next slide, but we call it the free flow speed. Free flow speed is what? Maximum speed. Okay. Now, so we have jam density, and we have capacity, we have free flow speed, okay, and then we have one more, which is this one, critical density and critical speed. Now this is critical density. At this value, what do we have?
Capacity.
Capacity. Which means what is maximum? Maximum flow. So when you reach maximum flow, you will have some density. And that density is known as critical density. We know one more density, which is jam density. Okay. Now which one is higher? Jam density is higher. Which one is good? Critical. Okay. Jam is only good for eating. Okay. Not on the road. Maximum speed. What did we call it? And capacity is what? Maximum flow. Okay. So when you reach maximum flow, there will be a speed. And that speed is known as critical speed. Okay. So we have two speeds. Free flow speed, critical speed. Okay. Which one is higher? Free flow is higher. Which one is better? Free flow. Come on. They are doing F1 to have critical speed. They want to have what? What? Which one is better? Free flow. Free flow is higher. You want more speed, right? More speed is good. Whatever.
It's one time.
One time. He will die, and that's it. Less cars on the road. I'm saying which one presents a better traffic condition. Free flow. Okay? Clear? Okay. Now every graph you see has two parts. One has a solid line, the other one has a dotted line. Solid line they call as stable. Dotted line they call as forced. Okay? Now what's the difference between them? When do I have the solid line? When do I have the forced line? Because it is, what's the difference between them? At which point they change? Capacity or the critical value, right? Okay. After capacity it is forced flow. Why we call it forced flow? Because now you are in the queue. So your movement is forced by others. You move when they move. You are slow because of them, and so on. Okay, so we call it forced flow. So in all the graphs you see, after capacity portion is forced flow. This one, this one, this one, and so on. There? Okay. Okay, now this is a graph between what? We have speed here and we have flow here. Okay, I showed you a speed flow curve, right?
Yes.
So this is your life in UOB. Very smooth. It goes up and down, but very smooth. Okay?
Sure.
And this is your life after UOB. Broken. Get it? Okay? That one was a simplified curve. The previous one is a simplified curve. This one is more practical. Okay? This is what actually happens in the field. And you will use it, you will draw it for your term projects. Okay? So, now you can see here, this curve is divided into how many portions? 1, 2, 3, 4. 4 regions. Each one is different from the other, right? What is happening in the first region? We have free flow speed and the line continues, right? So the speed is free flow, but the flow is increasing. The flow keeps on increasing, but the speed doesn't decrease. Okay, and this is what actually happens. Drivers are not keeping account. Okay, one car entered, I should reduce my speed. It doesn't happen like this. Okay, you reduce the speed when you start to feel that there are too many cars around you, right? If you don't have this feeling, you keep on same speed. Okay, the high speed. Okay, so this is what they call as because of the aggressive nature of the drivers. Okay, until they, what I'm saying is they feel that now I have to reduce the speed. Before that they are feeling very comfortable, so they go at high speed. Okay, so this is what they call as the aggressive nature of the driver. Okay, so in the first region, no speed change even if the flow is increasing. It continues till a point which we call as a break point. So till break point, the speed doesn't change. Okay, so there's the point of flow up to which the drivers continue at free flow speed. They don't feel the change in flow. Okay, so they don't feel the need to slow down. Okay, then region 2 is a curve. It's a smooth curve. So flow increases, speed decreases. Okay, it happens till what? Capacity. Okay, so till capacity, the speed decreases, flow increases. Okay, then at capacity you see what happens. There's a drop, a sharp drop, right? Okay, the flow changed this much, right? Okay, and the speed, even without the scale you can see this. Okay, this much flow and this much speed change. Okay, so it's not gradual, it's very, very sharp. Okay, here no change in speed, here gradual change in speed, and here sudden sharp change in speed. Okay, there. Okay, so this is what they call as the Q discharge flow or Q discharge region. Now what is happening? You just reached capacity. Okay, so the drivers behind you don't know. They are coming at 80-100 kilometers per hour. Suddenly they come and they see now the Q has started. So they go from 80 to 20. 0, okay. But there's a sudden dip, right? When the Q starts, the Q has just started, drivers don't know. Okay, so they are still coming at very high speed and suddenly they drop the speed. Okay, so this is this portion, region 3. And after region 3, region 4, again a smooth curve. But what is happening here? Flow is also decreasing. The speed is decreasing, the flow is decreasing. But now the Q is long enough so everybody knows. So they are already coming at slow speed. Got it? Clear? Okay. Now the equations which I showed you up till now, with the spacing and density and V equals to S into D and these graphs, all these things are telling you about the behavior of traffic, right? How traffic moves. And if you change one parameter, what will happen to traffic, right? This is what they are telling you. So any set of rules or any relationships which tell you about the working of a system, we call it a theory. A theory gives you rules, it gives you relationships, it gives you models and equations about a system. Okay, so all these figures and rules and the terms which we have discussed, they are part of traffic flow theory. Any mathematical relationship between traffic flow parameters is part of traffic flow theory. So whatever we have seen up till now is part of traffic flow theory. Okay, and this was given by my childhood friend Ruth Greenshields. Okay, in 1930 we used to play together. Okay, then he became a scientist, I came here. Okay, now how did he start? Okay, he started with the speed density curve. His proposition was, if you get speed and density data, plot it in a graph, and this graph will be a straight line. Okay, this graph will be what? A straight line. Okay, now do we know the equation of a straight line? What is the equation of a straight line? Sorry? A plus bx. Okay. Now I want to do this equation or develop this equation for this graph. What is my y here?
Speed.
Speed. What is my x here? Density. What is my a here? What is a? What is a in general? What do you mean by a? A is supposed to be what? Number what? What constant? Which constant? Can I put 2 here? Number of vehicles. Should I put number of vehicles here? I don't know. Number of vehicles is not a constant, right? Can it be a constant? No. So, you gave me the equation, right? A plus bx. What is a?
What is that?
Huh?
What is that?
This is what I'm asking.
Yeah, I was asking.
In the equation of a straight line, what is this constant?
Slope.
No. Slope is, okay, since you said it, slope is b.
Slope is B.
Slope is b. So a is what? Now everybody is b. Okay.
Speed. Speed.
Which is speed? Any value?
Higher.
65.
Jump.
What's speed?
Which is speed? Yeah, the highest one.
Why is speed?
Huh?
Why is speed? Why is speed?
Y is any speed, right?
Yeah.
But I'm looking for a constant value now. Which is speed?
About speed.
No. Huh? From where? From the graph, yes, but which value?
64.
Why 65?
Because
Because the maximum and the
Because it's a maximum.
in this day.
No, maximum is 70.
No.
Why not 70?
The point is.
The point. Which point?
There are no cars.
The maximum point.
There is no
The maximum point.
There is no car.
They call it the intercept. And it's written. What a joke. Okay? Not that. This is, they call it the intercept. The point where the y-axis meets the curve. Intersection. In the other section they were calling it intersection. Whatever you understand. The point where the line meets the y-axis. That is supposed to be A. Okay? So the line in this graph, the line meets the y-axis at 65. Yes. In this graph. Okay? Will it always be 65?
No.
This is why I'm trying to explain that you don't, just don't see the graph and put 65 always. Okay, it's not always. What is it supposed to be? The maximum point where the line meets the y-axis. It is 65 here. Okay, so I will write 65. Okay, and what did I say about b? Slope. Slope is y upon x, right? Y upon x. Y is 65 and x is 110. Okay. And one more thing. Why did I put minus here?
Because the line is decreased.
Yeah, because the line is,
The slope is minus.
the slope is minus. Got it? It's going downward, right? Downward is negative. Clear? Now in this equation you take 65 outside, you will have
Okay.
clear? Any question? So according to Bruce Greenshields, and we still go by his assumption most of the times, if you plot a graph between speed and density, you can develop the equation using the straight line equation, y equals to a plus bx. Okay? The graph can change, meaning a and b can change. A and b can be different. Okay, but it will always be, according to him, it will always be the equation of a straight line. Okay. Now, we have seen this equation as well, right?
Yes.
Today, flow rate equals to S into D. Okay. And I have this equation between speed and density from Bruce Greenshield. So in this equation, I can replace the value of S with V over D. So if you replace the value of S with V over D, okay, so you will be left with this equation. Okay, I open the bracket, did 65 upon 110, and this is what I get. There. So I replace S with B upon D from the first equation, and then I open the bracket, and I divide the numbers, and I get this. Okay? Not okay. Sure. Okay. Then I can go back to the same equation again, and now I will take D equals to V over S. So instead of having D here, I can have V over S. Okay? So this is what I do. And again, you will open the bracket, take V on one side, everything on the other side. So this is the equation now between fluid and speed. Got it? Clear? This was 65 on 110. Okay, this number was 65 upon 110. 1.69 was 65 upon 110. Okay? So between speed and flow, I have what type of curve? Huh? Speed and density. I had what? A linear equation. It was a straight line. Okay? Between flow and density, it's a it's a curve, right? It's a second degree curve. Okay? And this is what I showed you earlier, right? Between flow and density. Okay? And then between flow and speed, again, it's a curve, right? So again, we have a second degree equation. Clear? Any questions? Okay.